Hello there everybody, Professor Tomney here, and I am back with another Chem Complete lecture on carboxylic acids. And today we are going to take a look at some of the different methods for creating carboxylic acids from a synthetic approach. So that is all coming up on the channel right now. Thank you very much for joining me today and using Chem Complete as your lecture series of choice. Let's go ahead and get started. And a general reminder, head on over to chemcomplete.com for any additional resources you may need. There's plenty of free help over there as well. So, what we want to take a look at today is the different methods that we can create carboxylic acids with. So we're going to take a look at some different starting materials and some different types of reactions and see how we can get carboxylic acids to come out of them. So some of this may be review for people that have gone through alcohol, ketone, and aldehyde lectures, things of that nature, but it's a good recap, and there usually is one that hasn't been presented up until this point, and it's a type of Grignard reaction that we'll get to here in a minute. Okay, so the first major way, and probably one of the most common ways that people know of, is to take a primary alcohol and to oxidize it. Now, when you do this, the oxidation must be strong. In other words, you cannot use the Des-Martin reagent, you cannot use PCC, because those oxidizing agents are weaker and they will only provide an aldehyde in response to the primary alcohol. They will not give you the higher oxidized version, which would be the carboxylic acid. Okay, so to give you an example of this, if I were to take a simple alcohol such as propanol, I could expose the propanol to one of the strong oxidizing reagents. Now there are several of these. KMNO4 is one. There's a bunch of different chromium-based ones. One of the most common ones is the chromium oxide here. And you utilize this in acidic conditions, so H3O plus is very common to find present as well. And if you allow that to react, what you will end up with is that that carbon that contains the alcohol, so that third carbon over there on the propanol, is going to become the new carboxylic acid carbonyl group, and you now have propanoic acid instead of propanol. So that is one of the ways that we can create carboxylic acids. Okay, another way is nitrile hydrolysis with an acid. So this is actually first usually covered when we get to the cyanohydrin additions for aldehydes and ketones, because you add a nitrile group to an aldehyde or a ketone with that reaction, and then it can undergo subsequent reactions. And one of those reactions is the hydrolysis with acid, and it turns that nitrile group into a carboxylic acid group. Okay, so again, keeping the carbon chain length relatively simple, let's go ahead and create a nitrile group here. Okay, so we'll do CH2 and then C triple bond N. So remember, that is your nitrile group. Sometimes you may hear it called cyano, a cyano group, but they're really referring to the same thing here. So the materials that are needed here are actually pretty simple. All you need is some concentrated acid, and then you ideally would want to heat this as well. And the result that you should get is that that will drive this forward into becoming a carboxylic acid. Now when you do this, the carbon associated with the nitrile group becomes the carbon that will host the carbonyl for the carboxylic acid. Okay, so that is another option that we have there. Now the third option, which I was mentioning a few minutes ago, is a Grignard reaction. Now Grignard reactions will typically involve secondary alcohols coming about from aldehydes or tertiary alcohols that result from a Grignard with a ketone. However, you can use Grignard reactants with carbon dioxide, and if you follow up with the acidic rinse as you normally would in a Grignard, you will end up with a carboxylic acid. And I'll show you what I mean mechanistically here. Okay, so for this, we're assuming that you already know what a Grignard reagent is here. Okay, so let's just do a simple one. We'll do CH3 MgBr. Okay, so the methyl magnesium bromide will be our Grignard reagent. And then instead of an aldehyde or a ketone, we are going to react this with carbon dioxide. And I'm actually going to draw the carbon dioxide out just so that I can show you the mechanism that will occur here. So keep in mind that when we've got a Grignard reagent, you're really dealing with something that's more along the lines of this is an extreme partial positive to the point that it's almost a cation, and this is an extreme partial negative to the point that it's almost an anion. So what we expect is that this methyl group will come in and will attack the carbon in the carbon dioxide, and then one of these, it doesn't really matter which oxygen because they're both symmetrical, but one of them will take a set of pi electrons and we'll create the lone pair there. And let's go ahead, we'll actually add the lone pairs just so we're keeping track of them and doing good electron bookkeeping, as it were. Okay, so the result of this is then going to be that I would have, well, the CH3 group has come in to attack the carbon. Now that carbon has a double bonded oxygen, right? Because we can see that over on that side. So I'll make sure that I give it its double bonded oxygen. And then it also has this single bonded oxygen that has an extra set of electrons here, right? So that would have a minus formal charge on it. Now, if I take a look at this, this is nothing but the conjugate base for a carboxylic acid. So if you remember when we normally do Grignards, right, it's going to be, okay, step one is going to be whatever your Grignard reagent is. You react it with whatever other compound you're trying to, utilize the Grignard with. And then two, we always utilize with two, right, H3O plus or H2O. We give it some sort of a workup so that there are some acidic protons present. And so you can do that here, where you can basically say, okay, and then in the next step, I'm going to utilize H3O plus, and this carboxylic acid will then go ahead and take one of these hydrogens. Those electrons will go to the oxygen to create neutral water. Well, what do we end up with? We've got CH3, C double bond O, and then you've got the OH group, right? So there you go. This is a carboxylic acid, acetic acid. And you can do this with any type of Grignard reagent and CO2. So there's a large, versatile number of carboxylic acids that you could build, provided you have the correct Grignard reagent on hand and the CO2 available to react it with. Okay. Now I saved this one for last because it's highly specific. If you have studied aromatics before, then you have probably come across this reaction, but it is only going to work for creating carboxylic acids on aromatic systems. So the reason I save this for last is because it's more like hyper-specific. So in other words, you can't use this reaction outside of the context of an aromatic system. Okay, so the way that this would work, just as a refresher, I've got benzene, which is our most common aromatic system in nature, but also in general that we study in organic chemistry. Okay, and then we use what would be called the Friedel-Crafts alkylation, right? So I've got some sort of R group and then a Cl group, okay, and then I've got AlCl3 as a catalyst, and then that's going to put on some alkyl group to the ring, right? So then I've got some R group on the ring. So like, let's say that it's CH3Cl, then this would be a CH3 on the benzene ring. It would be a toluene. Okay, so then, and I'm going to put a mark here, and we'll come back to what this mark means in a minute. Just put a little asterisk there. Okay, so then after that, you're going to go ahead and you're going to expose it to a strong oxidizing situation, which will be KMNO4 in H2O. And that will result in taking your alkyl side chain and turning it into a carboxylic acid. And it doesn't matter how long the side chain is, it will always just give you this carboxylic acid back. So this would technically be benzoic acid. Now this could possibly occur with other things on the ring where it wouldn't just be benzoic acid, but you'd have other substituents. Okay, but this itself is benzoic acid. Now, why the asterisk up here? Okay, so the note that I want to leave for this reaction here is that whatever your R group is, okay, it must have hydrogens, okay, on the carbon attached to the benzene. Okay, so the carbon attached to the benzene ring. Okay, so in other words, just to give you an extra example here, if I had, let's say, this aromatic ring, and then the group that I had looked like this. It was a T-butyl group that was coming off of that aromatic ring. Well, even though those CH3s do contain hydrogens, the carbon directly attached to the benzene ring does not have any hydrogens available. And so this reaction, the KMNO4 step, if we attempted to do the KMNO4 with this compound, would fail. You would just get that compound back. So you have to have, whatever the R group is, the carbon that is directly attached to the aromatic ring must have a hydrogen on it. And that's really the only stipulation that we need for this particular reaction. Okay, so those are 4 different ways that you can synthesize carboxylic acids using a variety of different reagents. So I hope that this lecture was useful. Remember to hit the subscribe button if you want to stay up to date with future lectures. Drop a like because it helps to support us with the algorithm in the channel. And as always, if you leave me comments in the form of questions or you just want to show your support and say thanks, that's cool too. And I will get back to you as soon as possible. Head on over to Chem Complete. We've got lots of resources over at chemcomplete.com. You can check out the guides for purchase there. Only $5, $10 for most of those guides. Very affordable, and they'll help you get you through your studies. So that is it. I am signing out here, and I will see you guys in the next lecture.